So I guess this third session is the session in which I earn my keep because it's a school about out of equilibrium. And now it's the first time that I'll really plunge into that subject here. So if you thought the last time was fast-paced, I think this one is going to be, you know, a good test of the skills that you learned last time to keep up with fast-paced stuff. As usual, you know, please interrupt me with questions if you have any. And I'm really, really happy to give you more details about the stuff that I'll sketch here. So one of the things I'll try to do here, again, is just flash a huge stack of stuff before your eyes to mostly pique your interest and, you know, maybe fuel barbecue-style discussions about what can be done from this point onwards. Okay, so, but maybe this is also the kind of most fun bit of it all, because it really feels quite open-ended, and it really feels like something that can be perhaps talked about differently 10 years from now. Yeah, so what I'm telling you today, hopefully, is just like the precursors of many, many things that will come to pass in the coming years. So a bit of motivation. In 1909, Mr. Stevenson described a device in the scientific literature that probably had been known for hundreds of years beforehand, namely a rigid pendulum. So you've got a mass coupled to a rigid rod here. So incompressible, this really stays fixed length. And if you vibrate this thing at a sufficiently high frequency, you will create a state of equilibrium with the pendulum in the upwards position. The fun thing about this is that it was theoretically described only in 1951. You would have thought that people from classical mechanics a couple of centuries before would have been able to do that, but no, that is really like you know, second half of 20th century. So Piotr Kapitsa described that. Those of you who like renormalization, I would qualify this as being the best example in which integrating out high energy degrees of freedom gives you effective low energy degrees of freedom with interesting properties. Okay, it's a nice little mechanical thing to do. I'm a theorist, but actually, so usually people say, oh, you know, I'm a failed this, I'm a failed that. Well, I'm a failed engineer. I'm a theorist because by accident, what I really, really like doing is to build stuff. So at home, I have metalworking machines in my shed, and I built this Kapitsa pendulum a little while back. So just to demonstrate that this thing actually works, if the video can start. Yes. So the vibration frequency, it's about 20 hertz for that kind of size. You really just see that. You know, it's not perfect, but it does work. The pendulum really has stable oscillations in the upward position. You know, at the barbecue, I can explain to you how you can very, very easily visualize why there is a Hooke's law for this. Maybe I'll leave that for the barbecue, yeah, as a kind of planting thing. I could do it here. But we've got more complicated things to talk about. Why do I show this example here? It's because we physicists have the unfortunate tendency to look at systems in equilibrium. Namely, you tune parameters, you let your system relax, and you see what you get. Unfortunately, this is greatly limited as compared to the other possible phases of matter that you could stabilize if you were driving them intelligently. So the motivation here is that thinking about many-body quantum systems, perhaps there are things that we can do to them that allow them to develop correlations, properties that would be otherwise inaccessible in equilibrium. Okay, that's the kind of general storyline about this. Now, what I'm going to do today is give you examples which fail to do this, but perhaps constitute baby steps towards eventually being able to do stuff like that. I'll talk about progressively more complicated situations where we talk about things out of equilibrium. I will talk about essentially releasing prepared states in certain systems. So prepared states and quantum quenches, in a sense, they're the same thing. I'll talk about effective ways of understanding out of equilibrium things from integrability using notions of quasi-solitons and how generalized hydrodynamics comes from that. And at the end, I'll show you a couple of examples of Floquet dynamics, so truly driven systems where we can say stuff based on either exact calculations or drastic simplifications. Okay, so there's going to be a lot of talk about quantum quenches because that's really the place where we made the most significant progress in Amsterdam on these things. Okay. Prepared states. Well, so what are we trying to do here? We're trying to do out-of-equilibrium physics from exactly solvable models. And of course, we know how to prepare ground states, but there are also cases in which we can say, let's prepare a state which is in itself not a state that you would obtain in equilibrium. But I know how to write it in terms of the eigenstates of my Hamiltonian. And I can just declare that that's my initial state, and then see how time evolves or what properties it has. So I'll give you a couple of examples of that here, based on the Lieb-Liniger model. There's a thing called the Super-Tonks-Girardot gas. So what is this? Let me take Lieb-Liniger, but let me take attractive interactions in the Hamiltonian. So there exist bound states in this system. Atoms are able to find exponentially localized bound states, just like an atom. Now, the thing I'm doing here, which is special, which is due to Grigori Arstrakharchik and others, they invented that idea. The idea is that I'm going to start from a repulsive gas, but I'm going to put this repulsion to be infinite. Therefore, my state for that system of bosons is really the absolute value of a Slater determinant of fermions. It gives me a wave function. I mean, we have great specialists of Tonks-Girardot gases in the audience. The super-Tonks-Girardot gas starts from, in this case, the ground state of infinitely repulsive fermions and suddenly changes the Hamiltonian to infinitely attractive bosons. But the wave functions match 1-to-1. Okay? So it's a direct eigenstate also of the C minus infinity Hamiltonian. The only difference is that there exist these bound states then that can be accessed by perturbation. But these bound states have lower energies. So you're not anywhere near a ground state. You're in a very highly excited state, but it is the lowest energy, purely gas-like state in the system. No bound states. And then, because I know how to compute correlations in a Lieb-Liniger model, irrespective of what C is, I can compute correlations on such a state. So I'm just showing you some work that we did on this. The correlations look a little bit like the Lieb-Liniger one. However, they have a completely different weight distribution. So this is density-density correlations for this super-Tonks-Girardot gas. They have a different weight distribution as compared to the repulsive gas. You remember the repulsive gas, it had a very strong correlation in the type 1 branch. The attractive gas, so the super-Tonks-Girardot, has two features. First of all, much stronger correlations at this, this first incommensurate point here. But it also has negative energy contributions to correlations that correspond to intermediate states in which bound states are created. Okay, so that's just a baby example of something that would perhaps pass an easy test of qualification for out-of-equilibrium things. It's not an equilibrium because the equilibrium state of the attractive Bose gas is to bind everybody together. The ground state of the attractive gas is all particles bound together. But the energy of such a state is dramatically to minus infinity down there, and is therefore inaccessible. Okay? So really what we're doing here is correlations on a metastable state of interacting atoms. Ironically, it is, in principle, experimentally accessible because, like, you've been exposed to now, experimentalists are able to tune the interaction in these optical lattices in some cases, and for them, flicking the sign of an interaction parameter is just something that they can do by just tuning some extra potential. Okay, so that's the fun thing of these things. First example of what we have. Now, I'm going to move to another example, which is perhaps more deeply physically motivated. I flashed the slides of David Weiss's quantum Newton cradle experiment. So what is this? You've got atoms in an optical lattice, and suddenly you do a so-called Bragg pulse. Namely, you put a big cosine potential from a field of light that essentially, so there's a big cosine that suddenly appears, and depending on their precise position, the atoms will be pushed either left or right very strongly. So they get a kick at plus or minus k corresponding to the light field. So that's what happens here. That's t is equal to 0 just after the Bragg pulse. So what do the atoms do? Well, part of them goes left, part of them goes right. They climb the long-scale parabolic potential confining them to the one line, and suddenly they stop, they reverse, and they start moving towards each other again. And they collide, and then they keep doing that. And the whole point of this experiment is that you can do these cycles hundreds of times with seemingly no relaxation in the system. If you're colliding a three-dimensional gas, after 3 of those collisions, you would have a static blob in the middle with a momentum distribution that has relaxed back to the expected one at that temperature. But in 1D, these oscillations persist. Okay? So what I'm going to do is I'm going to try to cook up a state representing this initial state here with my integrable model. What is this state here, which is essentially the same as this one here? It's a gas composed of atoms that are either moving very strongly left or very strongly right. Okay? So in terms of a kind of pictorial representation of it, looks like this. Yeah? So one goes one way, one goes the other way. And now what I do in my beta ansatz is that I interpret that state as being created by a doubled up Fermi sea. So you've kind of come across these things. Some of you saw Andrew's poster and GHD, he's talking about split seas and that sort of thing. Okay, so I think of all my contributions of the last 15 years to physics, I'm most proud of this one here. I baptized this the Moses state. Yeah, because you take a sea and you split it. So the point of the Moses state is that it's completely codified in terms of quantum numbers in my beta ansatz. And therefore, I can use that as my initial state and compute correlations on that state. Note that this is a state that has very low entropy. So you imagine that there are many, many occupied states here in the left and right seas. So what that means is that when I compute correlations, I just get a kind of glorification of what occurs with a single sea. I've got different branches coming from different types of excitations. Maybe I'm creating particle holes close to one particular edge. Maybe I'm jumping from one edge to the other, and that hops me in momentum from one of these things or the other. The interesting thing is that all these thresholds are completely described from integrability, and the size of the correlation is also computable from integrability. But moreover, you can make a very good correspondence with Luttinger theory here, despite the fact that you're very, very highly energetic. Why? Because Luttinger theory is only contingent on the existence of edges. And here, I've got many edges at different momenta, but I do have edges. Therefore, that creates for me all the degeneracies that I need to apply Bosenization. I can take Thierry's book, and I just put the right KF in there, and I compute my V, or my U, if you prefer. I compute my K as well. And I've got, essentially, a multi-branch Luttinger liquid describing all the correlations for these things. Okay, so, but again, just from the general thing, I can also compute the correlations from Abacus, this numerical thing I presented to you. So these are examples of such correlations for different values of gamma, and you get just more interesting structures here. So in a sense, if you were able to do, say, Bragg spectroscopy in the quantum Newton's cradle as the gases collide, the idea would be that you'd get a kind of finite temperature version of plots that would look like this. But the correspondence hasn't really been made. Okay, so that's a bit of a mystery, how it looks like. You can also play the same game in quantum spin chains. So here I'm doing an experiment which is much more complicated. I'm creating a Moses state in a quantum spin chain. Precisely how I do that, I don't have the foggiest idea. However, it makes for nice, like Star Trek-like correlations with all these Fermi points, edge singularities, everything, again, describable by Luttinger theory. It's kind of funny because these are very, very highly energetic states. Nonetheless, they have essentially ground state-like correlations. You can plot the correlations obtained from integrability against those from the effective Luttinger theory. So here I'm really precisely following Thierry's textbook. I write the field theory, I compute the parameters of this theory from integrability, and I use the field theory to compute the correlations. And then on the other hand, I can just compute the correlation straight from integrability and compare the two. And essentially the two really coincide very, very well. Okay, so that's just like a fun extension of Luttinger theory to cases where it absolutely shouldn't apply, at least in a first reflex. Okay, so that's it. Now, we're going to have a long discussion about quantum quenches, which really is, I think, the most active. Yeah, question, yes. Yeah, I know. I didn't. I mean, technically, it's correct that it was. Yes, but in the meantime, it's like, indeed, yeah. So, yeah. Okay, so quantum quenches. The idea of a quantum quench. I mean, I guess most of you are either familiar with it or even possibly work in this. You just prepare a certain state, and then you do the time evolution under a Hamiltonian, which doesn't commute with the Hamiltonian that you used to create the initial state. So here's how it looks. Quantum mechanics tells us exactly what the time-dependent wave function is. I just apply the unitary time evolution operator onto the initial state. But the initial state is absolutely not a state that diagonalizes this Hamiltonian. Okay, so now it's kind of different from the prepared state logic because I require a very complicated linear combination of eigenstates. So I do have a non-trivial time evolution. The prepared state idea is really that I've got a single state here, but which is very highly energetic. Okay, so it's much more complicated to do this. And what do I want to do? Well, I want to do anything. I want to be able to compute time-dependent expectation values of whatever operator I'm interested in here. So it might be a it might be a single expectation value of something. It might be a two-point correlation function, whatever. These objects here will generically have a time dependence such that at first it's going to be very rapid dephasing, very rapid change of this, and stabilizing to something that it's going to be our task to compute. Okay, so the first question that you might ask is indeed how does the system stabilize and what does it stabilize to? And in this context, the literature is really quite extensive. And of course, as theorists, we just focused first of all on this steady state. Now this is where the realization of the difference between an integrable and a non-integrable model shows up. A conserved charge is really a dynamical constraint for your system. So in the presence of many non-trivial charges, your system is not going to be able to really explore phase space as if it was non-integrable. So the presence of these constraints has to be encoded somehow. And really, when you go back to your textbooks about statistical mechanics, that is also what people like Josiah Willard Gibbs tell you. You just need to take your constraints into account, and after you've done that, you can't go any further. You just assume a kind of equal probability for all the rest, kind of ergodicity. You explore this. So what's the difference here? Well, you make your name by calling it something good, like a generalized Gibbs ensemble, GGE, which is a kind of trivial extension of the idea of having a chemical potential or a temperature, but to other charges. So in normal systems, you'd preserve particle number, so there would be a chemical potential. You'd preserve energy, there would be a temperature. But now, to each and every one of your available conserved charges, you would associate an effective temperature or an effective chemical potential. I don't care, same concept. Okay, so this was really pushed forward in 2007, But really, if you look back at the literature, this was already talked about like 50 years before. And even if you go back, so John von Neumann himself kind of wrote things that are dangerously similar to this. Okay. I'm personally quite a critic of the GGE because I want to see it implemented in lots of different cases. And let's look critically at what the GGE requires. It requires, first of all, to encode all the initial data of your state into the values of these chemical potentials that you have here. Okay? So the determination of these parameters here involves the solution of a self-consistency set of criteria where you compute the expectation value in the initial state of each and every one of your conserved charges. That gives you a number. Once you've tabulated these numbers, you need to find the set of inverse temperatures, chemical potentials. I'll keep oscillating between the two. You need to compute the set of betas, which is such that when you compute the trace, you obtain the numbers that you had tabulated. Okay? So, why is this difficult? Well, first of all, the conserved charges themselves, I mean, I kind of showed you some of them, but not really many of them. In most interesting models with truly interacting systems, these charges are monstrous beasts. They're very difficult to handle. It's very difficult to compute expectation values on generic states. That's the first problem. The second problem is that this self-consistency problem is difficult to solve. And here, I know from experience, because the cases that I was looking at back then, I was expecting to be able to truncate this up to a certain level. So let's say I put the first 8 charges, and then I compute my betas. Then I say, surely I'm kind of close to the answer. I add a 9th charge, maybe 9th and 10th charge in view of like symmetries and things. Let's say I go from 8 to 10 charges. And then the chemical potentials that I've got with the truncated GGE up to level 8 have got nothing to do with the betas that I get when I do truncation up to level 10. And it does not converge. Okay? So the effective action that you have here does not have a meaningful power series or series expansion in these things, in most of the interacting cases. It just does not exist. And I'll show you an explicit example where it does not exist. So I was getting these infinities, these nonsensical things, and I was kind of getting desperate. However, there are literally hundreds, if not by now thousands of papers using the GGE. And why is that? It's because you can do this numerically, but most importantly, if you have a free system, then things are simple. When you have a free systems, for example, a translational invariant system, then your conserved charges are things like momentum occupation modes. So your whole problem here factorizes into one-dimensional problems of a conserved charge at that fixed momentum. So then you have an occupation being 0 or 1 at that momentum. And then the whole problem here factorizes into a problem with different momenta. So then you can do it. But the moment you try to do it with truly interacting models, it's much more difficult. Okay, so in practice, this is really, I would say that for truly interacting cases, it's really not understood in general. And another big weakness of the GGE is that this only codifies the state that you would obtain after waiting an infinite time after the quench. And of course, that's not what's experimentally accessible, and certainly not what's numerically accessible. What's experimentally accessible is something at finite time. Numerically also, you cannot go to infinite time on these things. So you can go to short times, but this is not accessible to GGE. So, looking for other things, then we tried to make some progress on these things. Sorry, that was a little bit fast. So what I'm going to talk to you about is a first example of a, I would say, controlled quench. And that's going to be from a specific state in Lieb-Liniger to, Lieb-Liniger at a different thing. Let me just define this properly. I guess this is dead. Okay, so what are we going to do? We're going to take as initial state the ground state of non-interacting bosons. We're keeping it simple at first. I'm going to have a ring, and on this ring I will create a number of bosonic particles, all of them at momentum 0. So it's an absolutely featureless state in all its correlations, in all its there's just nothing happening on this state, just filled. And at t is equal to 0, I will turn on repulsive interactions. So because this initial state here has extremely large number fluctuations in any little box that you would look here, there will be many parts of the wave function that will have particles overlapping each other at t is equal to 0. So when I turn on the delta function repulsion, those parts of the wave function obtain suddenly a stupidly high interaction energy. And in the course of unitary time evolution, the system will trade this interaction energy into kinetic energy, right? So I just have two particles, no interactions, and suddenly, bang, I turn on the repulsion. The particles will push against each other, and they'll trade the interaction energy into kinetic energy. Okay, so we're going to try to describe that. So the expectation is that from the initial momentum distribution function, which is a pure delta function at k is equal to 0 with weight number of particles, I'm actually going to time evolve to a state that has a non-trivial momentum distribution function, yeah, with a certain broadness associated to it. Okay? Is that cool? Yeah? It's like simple quench to understand. Okay, so it's a difficult problem to treat. And here, I have to mention again good friend Adilet Imambekov, because one of the very last things he put on the archive was a paper where he and his young people tried to apply, or thought they applied, the generalized Gibbs ensemble logic to this, because you could write Lieb-Liniger, you could look at the conserved charges, and you could compute those in the BEC state, because it just required some expectation values in a free bosonic theory. You could do that, simple moments of density operators and that sort of thing. However, it doesn't work, and the reason it doesn't work is because the conserved charges themselves, they have ill-defined elements when you try to interpret them between two different values of the interaction parameter. Namely, there are delta functions of space that occur with, argument 0 and in various powers, and even powers of the derivatives of these things. So what is the numerical value of delta squared of x is equal to 0? I don't know, but that's what you need, okay? There's no ultraviolet regularization in this theory. Yeah. And essentially, so it was funny because Adilet had a funny habit. He would take people in the community and privately give them nicknames that were kind of characteristic of what they were and how they were acting, and a deformation of their names. I'm not going to share any of these things except the one that he applied to me, as told to me later by Leonid Glassman. So for me, the name, I don't know how to pronounce it. Anyway, so his nickname for me was something like Hayut or whatever. What Glassman explained to me was that just meant the end of the road, the place where everything breaks down, everything becomes desperate, you fall off a cliff, you break your face, you die there. Maybe. Kayuk. Okay. So that was the thing. So when people contacted me, usually I broke them the news that everything was like complete disaster. So I had many conversations with Adilet. After I saw his preprint, I just contacted him. I remember we Skyped all throughout the night. My wife was very angry with me after that, but I said this was like dreadfully important. Yeah, and on the trip when he died, so Adilet was teaching himself the stuff required to understand this, and that's where it all ended. But anyway, so he didn't live to see the resolution of that thing. He just kind of died thinking that I was just a party pooper, yeah, unfortunately. Okay, so the conserved charges are not regularizable. You cannot do it. GGE logic is inapplicable when you take that. And I have kind of criteria to define when the GGE here is inapplicable. In a short summary, a simplified version is The moment you change the interaction parameter, GG is not going to work. You're not going to be able to do it. So one of the things you can do is deform the model, change the model, make it UV regular, namely go to a lattice. So there exists a lattice version of Lieb-Liniger, but it has a strange Q-deformed bosonic algebra associated to it. It's kind of strange quantum mechanics. And here you can apply a GGE logic, but you cannot obtain the GGE to, you know, a level of exactitude that you would like. You can only do the first few charges, and by the time you've done the sixth charge, you've run out of gas, and you think, you know, life is short, so you kind of give up. But anyway, so this was a collaboration with, again, those people just after Adilet had passed away. Okay, so I was still at that point looking for a different way of doing things. And now I'm going to try to present to you what I thought, and I still think to this day, is the proper way to do these things. First of all, I'll do it in pictures, and then I'm going to do it in equations. So, what are we doing? Well, we're starting from a well-defined state. And maybe the picture that you have of this state is that this is a given eigenstate of a given Hamiltonian, which, let's just draw it. I've got a Hilbert space here, and I put a coefficient of 1 on that state here. Everybody else is 0. Once I've said that, you can ask me anything you want. You want any correlation, whatever, I'll compute it for you because I know what that state is exactly. At all orders in system size, whatever, there is absolutely nothing indeterminate about this point. Now let me play the following game. I name a different Hamiltonian. I diagonalize it. I obtain its eigenstates. And I write absolutely precisely the same state in the basis of the eigenstates of that Hamiltonian. I haven't tossed anything away. Bases are complete. I really completely reconstruct exactly the same quantum state, but now in a different language. Okay? And there are some characteristics of this. First of all, under time evolution, any of these occupation factors do not change in mod amplitude. They only oscillate. So the only time dependence that occurs in such systems is dephasing between contributions coming from these different eigenstates. That's it. Okay? And most importantly, the sum of mod squared of all these numbers is just 1. Okay? It's like, it's just the way it is in quantum mechanics. There are certain things you can't argue with. So, I really like variational methods because sometimes they kind of allow to simplify problems. So, how to define a kind of variational method for computing what occurs? Well, so what you do when you do statistical mechanics, you write a Gibbs trace and you integrate, you sum over all the contributions, all the states, but you weigh those things according to the Gibbs measure, e to the minus beta h. And then if you've got chemical potential, etc. So energy somehow tells you how important a state contributes to a given statistical sum. So let's do the same here, but let me just say to hell with energy. What I'm interested in are states that have a high overlap. So I'm going to define a pseudo energy for a state. And the pseudo energy is going to be just minus log of the overlap. So if the overlap is 0, the pseudo energy is just infinite. If the overlap is very, very large, the pseudo energy is very low, or relatively low. And because of the preservation of norm, because all these things, all these overlaps mod squared sum up to 1, this thing, this new pseudo energy, is strictly bounded from below. Okay? And if my quench is non-trivial, then the distribution of these weights is going to have a certain measure of smoothness. As I take eigenstates in the neighborhood of each other, the overlaps also will be in the neighborhood of each other. So I can imagine a picture where I've got Hilbert space coordinated here on the plane somehow. Vertical axis, I plot this measure. This measure being minus log of the overlap, essentially. And here, there's an extra piece here. I didn't teach you thermodynamic Bethe-Ansatz. When you go to the thermodynamic limit, you need to count exactly how many states you put in these boxes that you need, that you need to sum over. It's called the Yang-Yang entropy. It's really just something that comes straight. I mean, it's like the Shannon entropy of the distributions that you need to characterize state. The important bit is this one here. So this pseudo-energy is driving the whole value of this so-called quench action. And now what occurs is that the steady state at t is equal to infinity is going to be the state at the saddle point, or the minimum, of this effective action. Okay? And you can find the location of that saddle point, of that minimum, by doing some variational stuff, just like you would do a saddle point approximation in field theory. You vary the distributions until you find the distribution that has exactly the right balance to make the contribution optimal. Okay, so that's the idea. So the t is infinity state is the state sitting at the bottom of this distribution. And now this steady state here, if you were able to do the GGE, would be the state pointed to by the GGE, if you were able to do the GGE exactly. However, if you think of the time evolution leading you to the steady state, what occurs is that at large times, the last time dependencies that disappear are the ones that correspond to interference between the steady state and states in the immediate vicinity of that steady state. Okay? So you can reconstruct the time evolution by, if you want, enclosing a little basin around your steady state and taking the contributions of those states into account. And the bigger you make this little puddle here, the more you can come back in time. So it's a funny circumstance. When you do numerics, you start from t is equal to 0, and you go to t is epsilon, 2 epsilon, and whatnot. You build it from t is equal to 0. When you do the quench action, you've got t is equal to 0, and then you start at t is infinity. And you work your way backwards. Okay? So that's the idea. Is it kind of clear for everybody, the logic? Variational stuff based on different information than what you would do in just normal thermodynamics and equilibrium. Yeah? You need a barbecue, don't you? Okay. So let me just take a few minutes to show you equations for this, because I want to make clear what the assumptions are for this. If you're completely lost, it's not going to help you. But, you know, and maybe if you know about integrable models, it's not going to make you happy, but I'll try anyway, okay? So what am I doing? Well, first of all, I've got a named integrable model. And in this model, I've got eigenstates. And for these eigenstates, I've got labels. These labels are these quantum numbers, these occupations that I define. Therefore, I can write a resolution of the identity operator in my Hilbert space as a strict summation over every single eigenstate available to me. Now, when I write the initial state, I can just decompose it in the basis of these eigenstates by using the overlaps. And these overlaps, I can choose to exponentiate them into this number here, which is just the log of the overlap. It's going to be in general a complex number. But here I'm not making any approximation, right? This is just exact. When I compute the time dependence, now this is the easiest step, because these are eigenstates of the Hamiltonian driving the time evolution after the quench. Therefore, the only thing I get is just the phase. When I compute a time-dependent expectation value, I just need to do a sandwich between bra this operator I'm interested in and get that. Okay? So I have a double summation over Hilbert space of matrix elements of the physical operator I'm interested in, sandwiched between eigenstates. So you already know from me that at least this element here I can compute with algebraic Bethe-Ansatz. Okay? Because it's the same stuff I do. I invoke Slavnov's theorem, solution of the quantum inverse problem, Slavnov's theorem, bingo bango, I've got determinate representations for these things. Perfect. What's these energies here? I can also trivially compute within integrability, because that's literally the easiest thing to do with integrability. I just compute the beta rapidities on a state, and I get an expression for the energy, and I get that. So this is all codified. So what's the difficulty, really? Well, I didn't tell you anything about the overlaps yet. We'll come back to that later. But of course, the big difficulty is the double summation over Hilbert space. Big time trouble here, because, double exponential sum here. Okay, so we're going to try to find tricks to make that more palatable. Okay, that's the problem, this double Hilbert space sum. Okay, so let's try to simplify that thing. First of all, I'm going to look at an object which I know equals 1, which is the norm of my state. And because I'm doing unitary time evolution, this norm doesn't change. However, when I write that sum here, using the notations that I have, I simply have a summation of these overlap coefficient mod squares, right? That's why you've got twice the real part of the overlap. Let's imagine now that I'm going to a thermodynamic limit where I replace this discrete sum over quantum number distributions into a functional integral over distributions of these quantum numbers. This is legit. I can do this. It's really a question of properly defining what I mean by these measures here, but I can codify that to all orders in 1 over L. No problem. And now I've got, this kind of entropy appearing here. It's just the fugacity, if you prefer, for this representation. And now I'm going to say, fine, the norm that I've got here in the thermodynamic limit is a functional integral over some beast here that carries the name quench action, okay, which is again the minus log of the overlaps with the entropy. And now I'm going to say, to hell with this, I am going to perform a saddle point evaluation of this functional integral, because my quench action here is assumed to have this isolated minimum somewhere. So what do? I take a variation of that thing. I invoke saddle point. The reason why I can invoke saddle point is because there's a prefactor in front of this, which is system size. So the parameter that guarantees the exactness of the saddle point evaluation is system size. So it's dramatically accurate. All corrections to this vanish exponentially in system size, as compared to the other stuff. So by solving this equation here, I obtain a saddle point distribution that characterizes this point in Hilbert space representing the steady state. Okay, and this is the so-called generalized thermodynamic Bethe-Ansatz, that you're doing like thermodynamic Bethe-Ansatz, not with the Hamiltonian, not with the energy, but with a different driving beast, the overlaps. Yes? Overlap. This bit here, the overlap part, is really minus log of the overlap for that state. That's right. Yeah, that's right. Essentially, it's like Anderson orthogonality catastrophe. So you will, I mean, if you kind of think about it, so the overlap between two states is going to be, if you write it in real space, some kind of integral over all the configurations of each of the particles. Each little box is going to give you a number that you exponentiate because you've got many boxes corresponding to many particles. It doesn't have always to be like that, but generically for a non-trivial quench, it will be like that. That it what, sorry? No, I mean, I'll give you concrete examples of this. So I'm really not saying that all quench situations, all overlaps scale like that, but for overlaps in the cases of quenches between two non-commuting not trivially related Hamiltonians. Generically, it's exponential minus system size times number. Yeah, right. And maybe once you see the concrete examples that I'll show you, you'll see where this exponential comes from. And I can give you other heuristic arguments for why it's like that. Okay, so that's the story. So at that stage, we would have characterized our steady state. And now going back to my formula for the time evolution, I now will apply this saddle point evaluation now to both numerator and denominator of that thing. Now in the denominator, that's the calculation we just made. In the numerator, I have another object here, which is the operator that I'm interested in, sandwiched between these two eigenstates. So here is where I need to make a first assumption. I need to make the assumption that these numbers here are small as compared to the extensive things appearing in the exponents. Namely, the size of these things does not shift the saddle point that I have in the numerator here. So the numerator shares the same saddle point as the denominator. So this thing here, I assume that the size of these things is sub-exponential in system size, and I can capture all the non-zero valued matrix elements here by limiting myself to kets that are small deformations of the bras. Okay, so the operator that I have here is unable to completely reorganize the thermodynamic state that I have here. It is able to create a denumerable number of excitations, but it is not able to transfer that many excitations that it changes the distribution of the particles that, or of the distributions that characterize the state. Okay? So any finite body interaction here with, one of the normal integrable models would have this characteristic here. So that means really that I can simplify this whole thing. Okay, I mean, these assumptions again can be verified for the particular cases that you have. Okay, so another thing is that because the bras and the ket then, due to the quasi-diagonality of these matrix elements, namely bras and ket do not differ thermodynamically, they differ in denumerable excitations. The overlaps also of these bras and ket states are similar thermodynamically with little order of one corrections associated to them. And again, you can verify that for the overlaps that you have. And if that's the case, it means that the saddle point of the saddle point evaluation of the numerator occurs at the same point as the saddle point evaluation of the denominator. And therefore, they fall off against each other. And that leads us to the final formula for the quench action, which tells you that, and now I'm making a strong claim, in the thermodynamic limit, the whole time evolution of the expectation value of a certain operator that is weak and thermodynamically finite. Weak, I've told you what it was, unable to redistribute things. Thermodynamically finite means that an individual matrix element here does not have an exponentially large in system size value, matrix element. Okay, it's more order of one things. This is always the case anyway for physical operators because of sum rules and things like that. Then in those assumptions, the whole time evolution of an observable falls back onto this formula here that tells you what you need to do is to compute the expectation value in the saddle point state, in the steady state. And if I put t is equal to infinity, I dephase and I'm going to go diagonal. Namely, I would just have the expectation value of O in the saddle point state. If I go to large but finite times, I need to include some excitations around it. And then I need to include their dephasings and their differential overlaps. But I'm still just summing these things here. And summing enough of these things here would allow me to reconstruct the whole time evolution. And the statement here from this is that due to the thermodynamic limit, this formula here is valid from t is infinity back down to any time which is not exponentially small in system size. So I can go back to 10 to minus 10 seconds if I want to, and still I will have a finite number of families of excitations to take into account. If I want to go to 10 to the minus 3,000 seconds, then I need to include a lot of stuff. But I don't really want to do that. Okay? So ETH, eigenstate thermalization hypothesis, is an, how could I say, unequal but not unrelated statement on this thing. So eigenstate thermalization hypothesis would tell me that essentially I could deform these things here simultaneously, Bra and Ket, and get the same value. So here the same kind of thing is used, indeed. So I did not tell you exactly how I defined these now Bras and Kets in the thermodynamic limit. I need to give you the formula for that, which I have, but I'm not going to show it here. So in that definition of these states here, then I can guarantee the applicability of that equality between different expectation values. So ETH is like almost a tautological consequence of the assumptions that we've made about this operator being weak. Right? So it's just more controlled because we've got the integrable models, we've got like the language, we can say exactly what we mean by these things. So if you want, I view it more that ETH is verified in these things. Not the strong version of ETH, but the weak version of ETH. The weak version of ETH I believe in, the strong version I don't. Okay. Yeah? Okay, so just a little bit of a message here. What I'm saying is that in systems, in circumstances which are out of equilibrium, the full time evolution can be reconstructed from a minimal set of data. So let's go back. We're doing equilibrium, and I'm trying to do, say, equilibrium thermodynamics of one of my models. What do I need? I need you to mention for me an equilibrium state. And for that, maybe you just need to tell me chemical potential, temperature. And then I scribble, 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 blank, I get my state. And on that state, I compute excitations. And I create an excitation, I let it move around, and I tabulate the value of the energy as a function of momentum. I get one function, which is the dispersion relation. And now I'm done because I can do thermodynamics. What do? I create one excitation, two excitations, three excitations, 27 excitations. I'm in the thermodynamic limit. If I create 37 excitations, the energy of the 37 excitation state is the direct sum of the individual energies of the individual particles, even if my system is interacting. Because the effective particles come from the background state. The new particles get a dispersion set by the background infinite number of particles, not the energies of interaction between the excitations and other excitations. These are subleading. So if I give you a single dispersion relation function, you can write down for me all the thermodynamics of this model. So from this single function, dispersion relation, you have all the thermodynamics. Okay? So here what I'm telling you is that if you now go to out of equilibrium, you need, of course, the dispersion relation of the excitations, but you need one additional function, which is the pseudo-energy, namely how the overlaps change for this excitation. So an excitation carries information about energy and information about the overlaps. And with these two functions, which again are additive, you know, when you create multi-excitations, with these two functions, you can reconstruct the time evolution. Okay? That's the kind of idea in this. Yeah, so that's what you need. You need the saddle point that you get from the generalized thermodynamic beta ansatz. You need the excitations in the vicinity of the saddle point state, which is just an exercise in integrability. And you need the differential overlap functions, which is this function here. So it's just looking at the way overlaps change when you do that. And of course, so you've got matrix elements here, so you need the kind of basis information for this. Okay, so that's the general philosophy. But once again, I'm just telling you a story. And you could ask me, where do integrable models show up in this story? Well, actually, nowhere. Nowhere. This is a statement this is a kind of approach which would work using any technology that affords for you a way of giving me the energies of state, or of writing trace over states as a functional integral. Okay? So, of course, we don't have many methods like that besides beta ansatz. But say you're doing purely numerical stuff. Then you could optimize your numerics directed by these weighing functions here. And I'm still, looking for someone to do that. So, so that's why I kind of titled the whole thing, from Newton's cradle to Gibbs's grave. So here is Gibbs's grave as advertised. Yeah, yeah. So I mean, essentially, what we're doing here is that we're just extending the very simple ideas that were used throughout, last century and a half to the out of equilibrium case by just tweaking them and adding some elements to them. Okay, that's the general idea here. Okay. Are we cool? Yeah? Like, I have no idea how you're all feeling. It's like, lunch was good and, yeah, question. Thank you.
The weakness of the operator that you are providing, is it somehow related to the locality of the operator?
If you had an operator that was strictly local in space, then it would be weak. But, this is, let me give you maybe an example of an operator that is not weak. Is if you compute, for example, the entanglement entropy over a finite fraction of your system size. So in that case, the presence of this operator would shift the saddle point. And then you couldn't use exactly the formula that I gave you. You would need to add another driving term in the saddle point equation when you evaluate the numerator. But if you were able to do that, you could still do the same thing, and it's just that you'd get a correction term to what I'm writing. Yeah?
Can you always compute the overlap?
Ha ha ha. Thank you. Thank you for the question. And here, the answer to this question is a resounding, disappointing, devastating, depressing, totally, no. Yeah, exactly. Exactly, yeah, so yeah, but I gotta live up to my reputation, right? So I'm gonna break everybody's party here, yeah? Okay, so no, and that's the whole cheat of the quench action. It's that I've thrown dust in your eyes, I've done as if I had access to these overlaps, but I don't. And before I do, I cannot do anything, okay? I can't even get started. So now, why am I telling you all these stories here? It's because in very rare circumstances, we have been able to do that. Okay? And I introduced for you the BC to Lieb-Liniger quench. And here are the overlaps for that case. So for the specific case of the BC state, which was, BC at fixed particle number, which was vacuum with creation operator of a boson at 0 momentum to the power n. For that state and that state only, we can write overlaps with beta eigenstates of Lieb-Liniger at finite C. Okay?
But is that you can't because you don't have any idea how to compute it, or it's too complex like numerically?
It's because I don't know. The only overlap, the single overlappable state that I know is the ground state of non-interacting bosons. Okay? And these are the overlaps. So they take the form of determinants of matrices of dimensionality system size with some residual functions here. So for example, great challenge for you young people. Let me take an arbitrary state of free bosons. So I'm telling you, I've got n bosons, and these n bosons are at momenta k1, k2, k3, kn. And I'd like to put whatever k's I want in there. Just free bosons. Then overlapping this state to the beta state, it's open problem. No idea whether that exists. There's no path integral representation for this. There's there's a kind of incompatibility between the free particle wave functions and the beta wave functions because of these, phase shifts. When you switch the order of particles, it screws everything up. There are very kind of appealing conjectures you might have for this, but most of the time you're disappointed. Yeah, so let's say that somebody was able to do this, an arbitrary free bosonic state overlapped with Lieb-Liniger eigenstates at finite C. Then the totally general problem is solved because, for example, if I want to go from C to C prime, what I do is I go from C to free bosons and then from free bosons to C prime. I just compose these things and that would work. So, but we don't know that. And we don't even know a simple, variation on this where maybe I put all the free bosons onto a certain momentum K1, or half of the free bosons on K1 and half of the free bosons on minus K1. Things like that, yeah? So we never found another. But if you find another, then immediately you can play this game. So the only one that we found for bosons is the BEC state overlapped with Lieb-Liniger states. That's it. Okay, so like fairly restricted, yeah? So your life is, usually I'm accused of like restricting my life to one dimension, but this is really a restriction to a point. Yeah. So it's like, yeah, so Thierry is, one dimension, but I'm, with age, I just go to 0 dimension stuff. It's like, how sad, yeah? It's like very depressing. However, this still buys you something, yeah? I can be king of my 0-dimensional kingdom, yeah? Because at that point, we now have all that we need to apply the quench action, okay? So what do I need to do? I need to compute my, my quench action, which means that I need to take the log of that thing. And generically, the log of that thing, I can now rewrite, you see, as an exponential of something that scales with system size and that has distributions with a driving term which looks like the log of energy, or lambda is like a momentum. So in energetics in Lieb-Liniger, energy is momentum squared. But here, pseudo-energy, what I'm using for the quench action, it's like log of momentum. Okay? So that is the quench action, exactly. And now I can do my variational treatment of this to determine what the saddle point is. So I just do the saddle point, and magically, we obtain an analytical formula describing the steady state. So this is, again, something that I haven't had the time to teach you. In thermodynamic beta ansatz, even for ground states, the number of analytic solutions of these equations that you get is very few and far between. In fact, there's only the spin chain in 0 field. For XXZ it works. It's essentially the only case where you can get an analytical form for an equilibrium state. But magically, in this quench case, somehow the simplicity of the initial BEC state has been imprinted on the steady state. And there's some analyticity in there that, we don't understand the deep meaning of this, but somehow it's there. Okay, so you get these like Bessel functions that describe that. But then the plots. So these are the distributions of rapidities that you have in the steady state as a function of the final interaction parameter. So when you start with a low value of the interaction parameter for the final Hamiltonian, then the distribution is still very peaked as the initial state was. But the higher you put the interaction, the more broad it becomes. Okay, so this is essentially the solution to the thing. And one of the things that you can do is compare these distributions to what you would get if you were only doing a Gibbs ensemble. Namely, you kind of have an equilibrium state at an effective temperature reproducing for you the energy content that you know exists in this model. So this is a proof that the steady state is non-thermal. Okay, so maybe I've got all these things here. Symptotics, and then for those of you who are interested in that, yeah, we were just talking about the tan contact and things. So again, you've got the tan contact showing up here, but also with these corrections. So I'll codify in here. So, so what is provided by this is an analytical derivation of what the steady state is, showing that the system equilibrates but does not thermalize. Okay. That's the interesting thing of this. Okay, so very happy with this calculation, but you know it's a calculation in a zero-dimensional space. Okay, so that's it. Okay. Now there's a second case in which we're able to do something. And now I'm going to do the same story, but with a spin chain. The quench I'm going to do now is I'm going to start from a purely antiferromagnetic state, a Néel-ordered state. And I'm going to time evolve that state according to a Heisenberg Hamiltonian with an anisotropy that I'll tune to what I want. So at first I'm fully ordered like this, and the time evolution of that thing is going to melt for me the antiferromagnetic order. So I expect this antiferromagnetic order to slowly disappear, because the Hamiltonian, these first two terms here, they provide me with exchange mechanisms smearing out the order that I've got here. Okay, so that's the idea. So can we treat that exactly? Well, I wouldn't be talking about it if we couldn't. So again, here, this is some stuff that that we spat out a while ago. The exact overlaps of the Néel state with the eigenstates of xxz, again, take a form which is reminiscent of the ones of the Lieb-Liniger, except that now you're on the lattice, and you can use some more refined treatments here to really prove that, that these are the correct things. So you get some monster here, but it's a completely known monster. I'm sorry? Okay, so if you just take this part of the kernel here and you write precisely the same matrix, then this is the so-called Godin matrix, which gives you the norm of a beta state. And it's called the Godin matrix because Godin is the first one to write that in his thesis in 1967. It has nothing to do with the Godin model. So the Godin model is a model of a kind of set of spins coupled together in a very defined way. But this result of Godin on the norm of the states is much more general. It's in principle applicable to all integrable models, at least all non-nested integrable models. So it's a result for the norm. It was proven by Vladimir Koryepin in a 1981 Russian paper using the algebraic beta ansatz. So before that, it was conjectured by Godin. But Godin was very good with integrals and summations, so of course he got it right. Yeah. Okay, and this, you know, I call it a double-dub Godin because it's just like the Godin matrix, except that the kernel is like symmetrized in the two arguments. Somehow this is important for these overlaps. Okay, so so that's the thing, and now you see the thing is really quite monstrous. We get these infinite sets of coupled integral equations with driving kernels that are absolute nightmares. However, magically, again, you stare at those things sufficiently long, and you are able to find an analytical solution to these equations. Somehow, once again, the simplicity of the initial state gets imprinted on the steady state itself. Okay, so and here the story is actually quite interesting because so when we first did that thing, we tried to do a GGE to verify these things, or to at least get the same thing. And when we wrote down the GGE, so, and again, there was a fun thing here. So for the specific case of the spin chain, we could carry out the GGE analytically using all the conserved charges generated for you by the trace identities that I showed you. You remember the logarithmic derivatives of the transfer matrix? We were able to carry that out in principle to infinity. Get an analytical form for the GGE coefficients, compute using that GGE some physical properties. For example, some, well, here's just distributions. I'll show you correlators later. So the strange thing was that the GGE was not coinciding with our quench action solution. So of course we were quite worried. And I first announced those results on a visit to Canada at the Perimeter Institute. And present there was Marcos Rigol. And we could show also in an explicit large delta expansion that the distributions from the GGE and from the quench action differed by things that really did not vanish. So I was talking to Marcos, showing him that thing, and he said, look, I've got a purely numerical way of computing some simple correlations in the steady state of that thing. So a kind of linked cluster expansion that he had that converged. So he computed the correlators. And so these are correlators, for example, you know, one-step distance for the longitudinal correlator. And the numbers that he got, they fell straight on the quench action result, but differed from the GGE. So he used to joke at that point that he had been on the paper that gave birth to the GGE, and with this thing, he would be on the paper that would give death to GGE. He said, you know, what a wonderful thing, you know, and both, yeah. So that was a mystery back then. You know, why doesn't the GGE work? Because manifestly the quench action, in its kind of non-negotiable nature of going through the overlaps, if done correctly, you know, gives you the thing. So that's why we kind of hesitated quite a lot to publish these things, because we weren't sure that we were doing everything. But at some point we became confident enough. We said, yeah, that's just it. GGE doesn't work. So now the story continues with this, where we managed to revalidate the GGE. And this is something that I'll just very quickly mention. In these spin chains, of course, I can write conserved charges of increasing complexity. And given these charges of increasing complexity, I can ask the question, yeah, where does this stop? Which ones do I really need? I can take my trace identities and go up to system size, and then I get a conserved charge that has operators everywhere in the system. But I can carry on if I want. I can take, you know, 2n derivatives, and 3n, and n squared, and up to exponential n. So where does it stop? So in principle, you would need to put all those charges in the GGE, okay? But you can cook up more clever combinations of quantum operators that are conserved by going back to your algebraic beta ansatz thing and saying, let me just consider more complicated auxiliary spaces. Let me just try to cook up other things that are conserved, but that are more easy to handle than higher moments of these charge identities. So the idea is that you've got some deformations that you can have for which you can do, again, the logic that we went through, allowing you to define quasi-local charges in these things. And these are quasi-local in the sense, I mean, I'm just flashing equations here. These are quasi-local in the sense that they don't have operators strictly confined onto, say, neighboring sites or sites up to 3. They have expressions that have tails that are very rapidly decreasing. So quasi-local in the sense you still need to do a summation over, you know, the position of the center of the operator, but then also the position of the tail of the operator, and this goes everywhere. But the tail is made of very, very small coefficients. So when you included those charges in the GGE, then you were able to get a reproduction of the quench action results. So somehow the quench action did the summation over all these local, quasi-local, whole hierarchy of charges for you. Yes? It depends on the charge. Typically, typically you'll have some exponentials showing up. But it depends on which ones you're looking at. Yeah. But they're kind of writable if you want. Yeah? I can give you a machine that will spit them out for you. Yeah. Okay, so that was the kind of story here. So the way to fix the GGE was to go not only the local charges, but the quasi-local charges, and then families of quasi-local charges until it converged. And in a sense for me, so we repaired the GGE with this, but also for me, we kind of proved the kind of maybe lack of economy of GGE for these things. Can you imagine the amount of work you need to do in order to do all these things to obtain something that you obtain directly from the quench action? So it's like showing, yeah, fine, you want to go here, and you can just do this, and then you're there. Or you can do GGE, and then blah, 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 and then you come, and then you finally get back here, and then you say, okay, but, what if I want time evolution from now on? Can't get started. Whereas with the quench action, you could, in principle, just try to reconstruct the time evolution here. So I really think, I'm going to die on that hill. I'll never win that thing. I really wish people stopped talking about the bloody GGE and got on with the business of doing it via the overlaps, because that's what you learn in first-year quantum mechanics, and this is now provably the most economical way of doing it. And even people who do numerics, here there's one thing which I have to say here, is that I don't need the exact overlaps. In the quench action, if I write my overlaps as exponential minus system size times a function, this function has an expansion in powers of 1 over system size. I've given you the exact function to all orders in 1 over system size. However, for the quench action, I just need the first term. If you just calculate the leading term in the expansion in inverse system size of log of the overlaps, then you can apply the quench action. So if you do numerics, you could say, let us compute overlaps between states. Maybe we're going to compute these things in some basis of matrix product states or whatever. And you try to just change your system size a bit and read off the coefficient that you get and use that as the driving term for your optimizer. Then your code will just go thump, 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 converge to the steady state. So you don't reconstruct a ground state, but you reconstruct a steady state after a quench. Okay, so I'm not going to do those numerics myself, but I wish somebody in the community would start looking at that, because I think this works. Okay, it would be nice to have that done. Okay, so yeah, so then that's it. Essentially, I had other things to say about the GGE, namely that the true physical conserved charges that you should think of are these distribution functions for the fundamental particles that you have here, but maybe I would teach you that if I had taught you thermodynamic beta ansatz better. Okay? So this is the bit about quenches. I'm not going to cut you from the barbecue, but I'm halfway through my talk. Okay? So I'm being recorded. I could, yeah, indeed. The recording doesn't see you, so you can slowly wander away. Yeah, still be here tomorrow morning, and yeah. Okay, so that's the story for quenches. On the one hand, I think the storyline, the method of the quench action is really appealing. It's a variational thing. Variational things are always like very kind of appealing somehow, because they do tell you that you've kind of hit the right principle to optimize to get to the answer. But, of course, it's contingent on knowing these overlaps, and that's where you're dead until you think that maybe, well, fine, I was looking for exact overlaps, maybe I don't need to do that, and now we should revisit whether we could compute the overlaps I was talking about earlier, but now just in their leading term in this inverse system size expansion. So maybe that is doable. Yeah, I don't need the exact thing. I could just write something that would give me that leading term in an exact way. Once I have the steady state, so actually with the overlaps, you're right. I would need to also have the first subleading thing in principle to be able to compute these differential overlaps. However, I think that, as usual in any function that has an expansion, the value of the first correction to the function is a feature of the thermodynamic function. Namely, if I know how to compute a thermodynamic distribution there, the thermodynamic function knows it's 1 over L correction. The 1 over L correction is a feature of the thermodynamic function. So if I need the correction, I compute it from the overall one. So I just really need the overall one. I can make that more explicit with things. Okay, so I really do think that even if we have only the leading term that I was mentioning in this expansion of the overlap coefficient in inverse powers of system size, that we can reconstruct the time evolution as well. Yeah. Okay, so that's the story about quenches. So be my guest. Try to find other states in spin chains. There's a slight generalization where you've got correlated states on adjacent sites that you can also treat with the same method, but it's by no means general, actually. Okay. So it'd be nice to be able to generalize that somehow. Okay, so that's it for the quenches. Now let me try in 5 minutes because that's what we've got. Let me talk about another way of doing out of equilibrium with these systems. And again, a slightly fun bit. We go back to 1834. We are in Edinburgh, next to the Union Canal. Or at least John Scott Russell was there, and suddenly this barge stops suddenly. And John Scott Russell sees an accumulation of water at the front, suddenly detached from the barge and start moving. And the bit of the story that I would accuse him of having made up, had I been referee, but there were no referees there, is that he had his horse with him. And he said that he followed this hump for like a couple of miles until the canal branched into 2 different branches where the thing dissipated. Now, in honor of John Scott Russell, they reproduced that hump in the Union Canal in Edinburgh a few years ago. I don't actually know in what year this was taken. But here's what it is. So it's a localized wave. It's not a Fourier mode. It's a localized mass of water that propagates at a fixed velocity without deformation. So solitary wave of translation, it's actually a really fun article to read. You can find it online. The idea is that this thing gave birth to what I would personally consider the most beautiful bit of classical mechanics from the 20th century, namely the classical inverse scattering method. So what is this about? This is about classical nonlinear time evolution equations. The most famous one is the Korteweg-de Vries equation. And here I have to say something which is anathema in Amsterdam, which is that, sorry for Korteweg and de Vries, both from Amsterdam, but this equation was first written by Joseph Boussinesq about 3 decades before. So we should call it the Boussinesq equation. But anyway, so what is it? It's a nonlinear equation, nonlinear because you see in the kind of velocity term here, there's some component here that shows up, meaning that big waves go faster. And due to the kind of strange dispersions that you get here, you get excitations in there that are localized and long-lived. And this is really interesting because I said that it's the most beautiful kind of classical dynamics or mathematical physics result. However, it is due to 2 pieces of numerical work. The first one being the Fermi-Pasta-Ulam and Mary Tsingu at work. Of course, she was a woman, so she couldn't be on the paper. Fermi could be on the paper, although he was dead. So, you know, in those days, it was even tougher for women in the thing. But anyway, so Mary Tsingu was the one who diligently ran all the computations of these things, where these, you know, these other people kind of gave interpretations. So she ran the codes. And what was that? That was about a system of coupled classical oscillators with different types of nonlinearities in their couplings. And at some point, they overran the simulation. And their objective here was to test ergodicity. So they would put all the energy in one of the modes and then let the system, because of its nonlinearities, distribute the energy to all the other modes. But at some point, like I was saying, they ran the simulation too long, and they noticed that the energies refocused on the original mode, which is absolutely against the idea of ergodicity. So, that was that. In that report, this was described but not explained. But then in 1965, the great mathematician Martin Kruskal, with his friend Zabusky, they did numerical simulations. Okay, so it's a numerical paper, 1965. Yeah, so really like punch card level stuff. But they did an image like this, where they start from a configuration that they will then time evolve, configuration with waves that are localized and that are like traceable. And then what do they see? They see colliding waves having essentially linear space-time paths until they meet another wave, at which point there's an interaction between these that kind of changes the space-time paths of these things. So Zabusky and Kruskal gave the concept the name soliton its true modern concept, namely it's a localized excitation that, that propagates with a fixed velocity without deformation, but most importantly, when it collides with another soliton, the two emerge eventually out of the collision without any particle production. Namely, soliton in, two solitons out. No particle production. And the important thing is that this thing here, you know, it's a game that you can also play in a quantum context. And here I'll flash these through very quickly. Let me do, I'm not even going to tell you about these complicated particles in XXZ. Let me do a wave packet in a spin chain. So let me just go to the image. This one here. So what am I doing? I'm taking a spin chain, and I'm creating on this one here a bound state of two downspins, and I kick it with a certain velocity. And at the same time, somewhere further away, I'm doing another wave packet of two downspins that I'm kicking the other way. So the two wave packets are propagating coherently, like a kind of classical soliton. But they collide at some point, and because of the interaction, you see, there's an attraction between these things. So this one here, when it's here, it's attracted to this one, so it accelerates a little bit. And when it emerges, it is on a space-time path which is slightly displaced as compared to the original one. Okay, so this is an experiment it's just scattering theory in spin chains, but you could actually simulate this on, you know, a cold atom device or a quantum computer whenever those become available. Okay? So it's quite interesting because you can compute the effect of anisotropy on these displacements here. So these are things that are there. And then literally in 1 minute, just give you the idea of generalized hydrodynamics. What is generalized hydrodynamics? It's essentially the idea of thinking about the time evolution of your integrable model initialized in a spatially non-translationally invariant state as a gas of like solitons colliding with each other and evolving in almost a classical way, really a kind of classical way. So I guess, you know, there are many posters about generalized hydrodynamics. Andrew can entertain you at the barbecue with his take on it, and many others here do that. So what's the idea? You just get this, this essentially continuity equation with an effective velocity that depends on the state in which you are at. And the simple illustration for this, you can do by going back to the Zabusky-Kruskal experiment. If you take one of the solitons, then it's got a certain velocity associated to it, which depends on the presence of other solitons. So if other solitons are present, it gets an effective transformed velocity due to the scatterings with the others. Okay? And that's it. So now, under GHD, time evolution becomes kind of a classical thing, like I said, and you can just play lots of games here. So here, just a thing that we published. So Jérôme Dubail is really the one who ran all these things here, published in a glorious paper here, glorious journal. So here, these are just phase space plots of a setup described with GHD, aiming to reproduce features of the quantum Newton cradle. Yeah, so it's really usual phase space thing where you've got position and momentum, and then harmonic motion is just circular motion on these things, and you see some dephasing on that. And maybe just as a final thing, so I was very disappointed because we published that before the big collaboration, and I was very happy that they ended up just seeing our simulations, because of course they didn't see a black hole. Yeah, so I'm going to drop the Floquet dynamics bit here, the private discussions on this. But what I would like to say is that although life as an integrabilist is hard, in the few and far between circumstances where it works, at least you get stuff which is interesting. So I hope many of you are going to at least look at the history of these things and what's been done in the last, say, couple of decades, and maybe find cracks, opportunities of things that are still open. I can give you a whole list of ideas if you want to try to break your face on those. But it would be nice if a new generation came into this and really helped keep the momentum on these things, because I think we're by far not done with the things that integrable models have to tell us. Right, so thanks for your attention. I'm stopping because I'm actually starting to smell barbecue-like stuff. No, am I the only one, or? Yeah, Tony.